what it means independence in terms of a continuous random variables. And as before, kind of the independence of random variables means that if you observe one random variable, then this will not affect the probability distribution of the other random variables. So it's kind of the chances that the other random variable takes some specific value remain the same. So this, in case of a continuous random variable, means that if you have a random variable y and x, and you look, say, at y, conditional probability of y given x, so, and here's y, and here's x, so so this is a conditional density, and so kind of it should be the same as the marginal density, so it should be equal to f of y of y. So this condition ensures that, well, kind of if you observe that x is equal to x, then still the probabilities, any probabilities for y have not changed from the original situation, right? When you didn't know anything about x. And so if you write it down, if you write down the definition for conditional density, so this will mean this thing. So just by definition, you write that the left hand is equal to joint probability, and maybe can write x, y, kind of it doesn't matter, kind of because we are here sure that it's density at x and density at y divided by the probability of the condition, so f of x of x. So this is by definition. This is definition of the conditional density. Well, and it has some meaning, of course, but kind of we define it this way. So it should be equal to f of y. So which means that f of x, y, so joint density, should be equal to the product of the marginal densities. Y of y. And we will take it as a definition just because it's symmetric. So before that we talked about, well, before kind of here in this equation, we talked about the independence. So we are saying that y is independent of x. Right? So kind of it's intuitive thing, but it says y is independent of x if the conditional probability of y given x is the same as the marginal probability. But from this calculation, it is clear that this is symmetric. That is, y is independent of x. It means that, well, x is also independent from y. So, and the definition just says that two continuous random variables x and y are independent if, so this equality holds. So let me kind of repeat it, but so it's just f of x, y of x, y is equal to f of x, f y of y. And so kind of this is the definition of independence. And so, and okay, so this is the definition. So they are not independent if they are, well, so if they are dependent, if they are not independent. So one thing to say, it's sometimes useful to to have some criterion which allows you to check whether the two random variables are independent. Right? And it's kind of small kind of theorem. So if you look at this on this equality, so it says you how you can check. So you're given joint density, how you can check that the random variable with this joint density is independent. You'll need to calculate marginal probability of one, random variable marginal probability of another random variable and check that joint density is equal to their product. So it turns out that usually it's not so complicated. Usually you have a you just need to check that you can write down the density as a product. So kind of a theorem says, so here's a theorem. So if joint density f x y xy can be written as a product. So f of x y is equal to, say, h of x multiplied by g of y. Valid everywhere in R2, right? So kind of for every x and y. So for every, so it's the same x and y. Then x and x large and y large are independent. So what it means? So kind of say, look at this. So here's an example. So say you have a f of x and y equal to this thing. So it's equal to, say, 2x if 0 is smaller than x smaller than 1 and 0 otherwise. Sorry, 0 smaller than x than y and 0 smaller than y than 1. So kind of for this 0 otherwise. So it's equal to 2x in this square. So you have a so here's x, y, so here's 1, say 1. And the density inside of this region is equal to 2x. So the range of this random variable is this square. Right? So so range is here. Outside of this range, the random variable is equal to, so the density of this random variable is equal to 0. It means that it never takes out values outside of this range. And so now you need to check that this is a valid random variable. So valid density, so that integral of this density over the whole range is equal to 1, but it can be checked that this is a valid random variable. So now I ask you the question, is it kind of random variable x and y independent or not? Then, okay, so in principle, you would need to calculate the marginal densities of them, of this x and y. So figure out what's the marginal densities. And check that the conditional, so the joint density is equal to the product of these marginal densities. Right? So, but in principle, I can say, no, it's easier kind of than that. It's kind of, I say that this f, that this f of x and y, so here's x and y large, is equal to, say, 2 times x. Right? And you can say this is a, so for our theorem, this is h of x, and we say this is g of y. So the h of x depends only on x. G of y depends only on y, and in this case, it's just a constant. Just kind of, well, the most important that it doesn't depend on x. Well, it also doesn't depend on y, but it's kind of, we can think about this as g of y, just constant. Okay, so, and well, so this is, this 2 is actually, And moreover, let me say that this is actually this is g of y more precisely, say, right? So because we also have this condition on the range, so we'll say that g of y will be equal to 2 if y is between 0 and 1, and 0 otherwise. And this h of x is equal to x if 0 smaller than x, smaller than 1, and 0 otherwise. So this is a plot of this. So this is our h of x. So maybe I should draw it immediately after under this. So h of x would be something like this one. Right? So this is just x, and g of y. So and it's 0 outside, and g of y just equal to 1, to 2. Okay, so this is a g of y. This is y. This is 1, and again, so it's 0 outside. And so, and you can observe that, well, this is the joint density is equal to the product of this 2 and x. G of y, it's not a density because the integral hours, it's not equal to 1. So it's not a valid density, but still it's the joint density is a product of two functions, and one function depends on x, another function depends on y, and so our theorem says that then x and y in this case are independent. All right, so this is useful. So you look at the function, check whether it is possible to these two functions are product. Is it possible to write down as a product, and you immediately know that whether it's the two random variables are independent or not. So here's a warning, So let's look in another situation. So let's look at the case when you have a f of x, y. So our previous situation that we looked at the couple of the previous lectures. So we looked at the situation 3x when 0 was smaller than y, smaller than x, smaller than 1, and 0 otherwise. Right? It's almost like a previous example. Right? So in previous example, it was 2x. But the important thing that the range here is it's a different range, and it's not a rectangle. Right? So it's not a rectangle range. So here the range is triangle. Right? So here you have this range. Right? So this is like that. And so this is the range in this problem. So this is what this inequality gives to you. 0 smaller than y. So y is greater than 0, x is smaller than 1, and y, so y is smaller than x. So this is the y equal to x, and our region is y smaller than x. So here we'll see that the region is a triangle. Right? So although this appears that this is a 3 times x, right? But it's 3 times x, but you cannot write it really as a 3 times x, because if you look at the value where the random variable value here, that the here the value of the joint density is equal to 0. It's not equal to the product 3 times x. It's not 3x in this point. It's equal to 0. Right? So it's not possible to write down here the joint density is a product of two functions. One of them is a function of 3, and another is a function of x. And so in this case, these two random variables x and y are not independent. X and y are not independent. Not independent. dependent. Right? And if you think about this, so kind of why kind of this happened that these two random variables are independent, not independent, then you observe that this has happened because this is a range is a triangle. So if we're independent, if it is possible to write down this joint density as a product of two individual joint densities, then it must be that the range is rectangular. Right? So it's like a rectangle, maybe infinite rectangle. Right? So maybe kind of it's like a quadrant, right? So it could be also like kind of like this thing. So this this kind of a region would be okay. So kind of if it extends to infinity, but it's still kind of like a kind of a product of two intervals. One interval in the x on the x line, another interval on the y line. These are two infinite intervals, but the region in the plane is a product, kind of Cartesian product of these two intervals. In this case, well, it could be independent if you write down is a product. If you write down the joint density is a product two function, one function is x, another function in y. But in this case, when the range, in this case, when the range is the a rectangle is a triangle, it's not possible. So x and y are not independent because the range of x and y, and the range, it's a support of a density function. So it's the set where the density function is not equal to 0. So the range range of x and y is not rectangular. Rectangular region. So kind of this gives you ability to check kind of whether the two random variables are independent or not very easily. You look at this and first of all check whether the range is rectangular. Right? If it's not rectangular, they are not independent, they are dependent. If it's rectangular, you need to look attentively at whether you can write down the joint density as a product of two marginal densities. If it is possible to write it as a product of two functions, not marginal density, two functions, one of them is dependent on x, another is depends on y. If it is possible to write it down as a product, well, you are done. If it is not possible, well, you probably need to prove that it is not possible. But if you kind of, sometimes it's more or less obvious that it is not possible to do so, then you can kind of say that the two random variables are not independent, so they are dependent. Yeah, so here's maybe, so it's an example. I will not go into go kind of rigorously about it, but kind of to say, so here's an example. So you look at the function f of xy, it is equal to say 4xy, y3. So then maybe another one f of xy is equal to 1/2. Sorry, 1/2 x cubed y, x cubed y plus x y cubed, and another one, so f of xy is equal to 6e minus 3x minus 2y. Right? So suppose these valid densities in rectangular regions. So rectangular regions means that kind of, so this is f of xy, so this f of xy is valid kind of, so if x is greater than a, smaller than b, y is greater than c, y smaller than z, and 0 otherwise. Nice, when a and b some numbers, a, b, c, and d some numbers, which in principle can be infinite, right? So minus infinity or plus infinity. So assume that this f of x, so this is kind of this all these three functions is a valid densities. So their integral is equal to the integral of the range is equal to 1, and well, kind of this is the range. Kind of the range is described by these inequalities. Okay, so now the question is, so are x and y independent? Okay, so kind of you look at this thing and I say to you, well, one thing is satisfied. The regions are rectangular. Okay, so what about kind of, are they independent if the regions are rectangular? So you look at the first one, right, and say, okay, so this is easy. So 4x squared y cubed is just equal to 4x squared multiplied by y cubed. So you say this is my g of x, this is my h of y. Okay, so well, it's a product of two functions. One is a function of x, another is a function of y. So somebody promised me that this is a valid density kind of, and that the region is rectangular. So kind of, so that means that this is a for in this case. Random variables are independent. So random variable in this case, x and y are independent. And so what about the next one? So kind of the next one says that the density is 1/2 x cubed y plus x y cubed. So this is f of xy in this case. And so, and you look at this and say, well, it looks like that it is not possible to write it down as a product. Well, in principle, you need to prove it somehow. And let me skip the proof. Right? So probably kind of, if you want a proof, I think that I proved it in the lectures which are on YouTube in the, from the previous year. And so it's not very difficult to prove, kind of just to show. If you assume that this is true, then you can find a contradiction. So if you look at some specific values of x and y, so at some point you run out in the contradiction. So well, not possible. And kind of from observation, you see, well, it's unlikely that I can write it down as a product of two functions. One of them is a function of x and another is a function of y. Not possible to write as g of x multiplied by h of y. Okay, so not independent. So which means that it's the same as dependent. So dependent. So it's just the same thing. Dependent. And so now what about the next one? So here's f of xy is equal to 6e minus 3x minus 2y. And well, in this moment, kind of you just need to kind of remember that this is exponential, right? So you can actually write it down as a 6e minus 3x multiplied by e minus 2y, just the properties of exponential functions. And so you factored this thing, so you factored this density as h of x, sorry, g of x and h of y. Right? And also I promised you that the range is rectangular, right? And that this is a valid density, so you know that these x and y are independent. Yeah, so it's very easy to check whether some two random variables are independent if you know the joint density, the upshot of all this discussion. Now, it's possible to go other way around. So actually it's used very often other way around. So you kind of have a model in which several random variables are independent. You kind of, well, have some intuition that they must be independent. Right? So you can write down the joint density for these random variables, and after that do something with this joint density, calculate some kind of density of some function of these random variables and so on. And so how it's done? Well, kind of if you have a if you have a kind of if x1, say x2, xn are independent, and their densities is f of x1 f of x2 x, so maybe kind of x actually, so they also were kind of, well, this is just x is just kind of, well, argument of the function, right? So, well, kind of, so f of xn of x is just a placeholder, right? So for the argument of this function. And so then joint density of x1, xn is the product of this thing, right? So it's f of x1, xn of now here x1, xn, right? So these are now random, different, and you write it, it's a product. So it's f of x1 of x1 multiplied by f of x2, x2. So this is multiplication here, multiply many times, kind of f of xn of xn. Right? So here's kind of, so here's an example. So if you have a so xi is a lifetime time of a battery. So, and you assume that you have a sample of these batteries. So you have a, say, 5 batteries. So n is equal to 5 sample of batteries. So if you have a sample of the batteries, you can think about them so that their lifetimes are independent from each other. If you know lifetime of one of them, well, kind of, if you already know the parameters, right? So then the life, so kind of, if you know the mean for each and mean of this random variable, then the lifetimes are so they rise around this mean, and they're kind of independent. Kind of the lifetimes of one battery, kind of, it doesn't affect what's the lifetime of another battery. So you can say that x1, x2, x5 are independent, right? And so, well, kind of, it's a lifetime. So a nice way to model it using exponential random variable. So when you have a time, and also often kind of it's exponential random variable. So we model as exponential with, say, unit some parameter. So mean is equal to, well, say kind of 30. So in 30, well, you can mean 30,000 hours, so I'm not sure. Let's say 30. Let's not talk about units. So it's exponential with the parameter beta is equal to 30 in some units. And so you can ask the question, what is the joint density? What is the joint density of x1, x2, x5? So, and well, kind of, it's, we just talked about how you can write it down. We write it, this is f. Let me skip the kind of subscript here, right? And just write it f of x1, x2, x3, x4, x5 in full glory, kind of. It depends on the 5, kind of, right? So, and it's equal to the product. So it's equal to 1 divided by, so maybe kind of in general beta, right? So here 1 divided by beta e minus x1 divided by beta, right? So multiplied by 1 divided by beta e minus x2 divided by beta, and so on until 1 divided by beta e minus x5 divided by beta. So if you multiply this together and use the kind of the law that product of exponential is equal to exponential of the sum, and we'll get that this is equal to 1 divided by beta to the power of 5. And here's e minus, okay, so here's x1 plus x2 plus so on plus x5 divided by beta. So, and beta is equal to 30. You can plug it in, but kind of, right? So, okay, so this is the joint density. Maybe the only thing we also need to say where it is valid, right? What's the range, right? So for x, so 1 greater than 0, x2, so greater or equal, maybe greater than equal, doesn't matter whether kind of greater or greater or equal. So this is continuous random variable. So, but kind of x5 greater than equal than 0, right? And 0 otherwise. So kind of, well, kind of this is a typical example, kind of, so it's usually used in this way, kind of, right? So you are given kind of a density of one random variable, you need to kind of find out what's the joint density of all of them, because after that you do some calculation on this joint density, right? So, and here's, you just need to write down this product. Okay, so, okay, so this is a, okay, so one more thing about the expectations. So as usual, right, as usual, you have this kind of the most important property of the independent random variables. So it's a theorem which we proved in the discrete case, and it's also valid in the continuous case. So if x and y are independent and say G so G and so H are two functions, and these functions map their real numbers to real numbers, right? So, and in this case, we well, there is some requirements on these functions, but this is kind of almost any function. So kind of there is a thing which is called measurability, kind of, but it's almost every function, continuous function, kind of almost every function is okay, kind of, right? So then we can write that expectation of the g of x multiplied by h of y. Right? So expectation of this function of two random variables. So this is g of x multiplied by h of y. So it's a function of x and y, just a product of g of x multiplied by h of y. So it turns out that it's equal to expectation of g of x multiplied by expectation of h of y. Right? And this is it's a consequence of a particular case. So in particular, so expectation of a product x multiplied by y is equal to expectation of x multiplied by expectation of y. So this is a particular case, but the general case is a consequence of this particular case, and the fact that if x and y are independent, then g of x, function of x, and h of y are also independent. Right? So this is what we talked about when we described discrete random variables. Right? Okay, so this is just a fact that we will use when we will talk about kind of. So now we will go to the covariance, right? Maybe before that is kind of, well, just a, I'm not sure. I've already talked about this before, but in principle, how you calculate this expectation g of x on h of y. So what it means for expectation of a function of two random variables. So in general, if you have some function of two random variables, so if you have expectation and here's some function, call it, say, well, maybe again h of x and y. So it's something like kind of could be something like sine of x squared plus y squared. I don't know, something like that. Right? So if you want to calculate it by definition, well, by definition one thing, but the most useful kind of formula for this is that this is equal to the double integral, right, of a range of x and y. Right? And here's h of x, y. So x small, y small here. Right? Multiplied by the joint density, xy, dx, dy. Right? So this is how you calculate it. Right? This should be clear, right? So it's just generalization. If you want to figure out what's the expected value of some function of two random variables, you take the values kind of this function h of xy and calculate the average using kind of integral, not the sum but integral average, using as a weights the density, the joint density of these random variables at the point x and y. So it's also weighted average, but now we take this weighted average not on the line but in the plane, with the weights equal to f of x or y. Right? So this is kind of right. So this is just explain what this means, expectation of g of x multiplied by h of y. Right? So now what about covariance? Right? So covariance. So it's a, well, so this is a repetition. So it's a particular measure, a measure of dependence. So everything goes now from now on as before, dependence. And it's defined like that covariance of x and y is equal to expectation of x multiplied by y minus expectation of x multiplied by expectation of y. And so if you look at formula here, and then you say that covariance of the two independent random variables is equal to 0, because, well, for independent random variables, this will give you 0. This difference will be equal to 0. And so if the two random variables are independent, their covariance equal to 0. Well, if they are dependent, well, sometimes it can happen that their covariance is 0, but it happens rarely. Kind of, it's something special situation, happens rarely, so it's useful measure. Right? And all the properties of the covariance that we talked before is the same. It's bilinear in every argument. Covariance of one random variable with a constant is equal to 0. It's symmetric. Right? So covariance of xy is equal to covariance of yx. So everything is absolutely the same. The only thing that it's kind of, to calculate it, you'll need to, well, to use densities. So what we'll do, maybe kind of just calculate it in one specific example. Right? But maybe kind of, well, since right, so this will be a lengthy example. Maybe let us at this moment kind of, well, stop and maybe make a 5 minutes break. Right? And after that, we'll look at this specific example. Okay, so small break. All right, so let's maybe start. So let's look at the specific example. So now this is our example that we always use here. So this is f of xy, right, is equal to 3x if 0 smaller than y smaller than x smaller than 1 and 0 otherwise. And just ask the question, so what's the maybe covariance of xy, and also correlation, right? So correlation kind of, well, it has the same definition as in the case of a discrete random variable. So what's the covariance and then the correlation? And it turns out, well, this is a purely computational exercises, maybe kind of, well, pretty routine exercises. So you have a function here, right, with this specific range, which is a triangle. Right, and you'll need to find the integrals over this range with some specific functions, right? So kind of what it's. So you'll need to find out. So if you want to apply this formula for in the definition of the covariance, right, so you'll need to calculate expectation of xy. So let me just show kind of the setup, right, and skip the kind of the calculation. So the setup, okay, so expectation of x multiplied by y, xy. Okay, so it's a double integral. So with this range, right, so this range of x, y multiplied by the density multiplied by 3x, and here's dx dy, so here's a range. But we'll need kind of calculate it. So we write it down as a repeated integral, and we'll need to choose what we want to do first, what's when we want to do, what's the inner integral, what's the outer. Say dy dx. Let's say dy dx. So dx will be outer, so x changing from 0 to 1. So from 0 to 1, and inner integral, in the inner integral, we just figure out, so if we fixed x, it's how the y is changing. So now we fixed x, so we are integrating over y for a given x. So now the limit of integration is from 0, and here's a point, this is a kind of, this is line y is equal to x, so this is a point which is equal to x. And so y, so here's 2x. So in the integral here as well, it's this kind of, it's 3x squared y. Yeah, after that you do calculations, so you integrate, pretty straightforward, and you'll get eventually, so let us make the first step in this integration. So the first step will be kind of, it's integral from 0 to 1. Here's 3x squared y squared divided by 2, and here's from y is equal to 0 to y is equal to x. Right? And so this thing should be integrated after that over dx. So will be integral from 0 to 1, 3x squared. Here will be x squared divided by 2. So dx. So, and well, it's kind of easy in this case. Maybe kind of let us finish. Here will be equal to the integral. So maybe not integral. So here you can write the antiderivative, 3/2, 1 divided by 5, x to the power of 5 from 0 to 1. So it's equal to 3/10. So kind of pretty easy integral here. Right, and now after that you'll need to calculate expectation of x. We already calculated it. So, but it's kind of an integral from 0 to 1, so the range of x. Here x multiplied by the marginal density of x. We calculated at some point it was equal to 3x squared dx. So if you continue this calculation, you will find that this is equal to 3/4. And now an e of y, so it's integral of the range of y, 0 to 1. Here was the y, multiply the marginal density of y, and this was actually, I think that it was 3/2 1 minus y squared dy. So now this is a little bit more complicated integral, but if you calculate, we found that this is equal to 3/8. Let me check it. Yeah, 3/8. And so, well, after that, you have a formula for covariance, right? So covariance, we will write it here, covariance of x and y is equal to expectation of xy minus expectation of x, expectation of y. So it's equal to 3/10 minus 3/4 multiplied by 3/8. And if you calculate it, then you'll get it. This is equal to 3 divided by 160. So which is approximately 0.1875. Right? So some number, right? But unfortunately, this number is not very meaningful. And so we know that this number, but it looks like small number, but we need to compare it. So it may be small because the variances are small, right? So we'll need to understand whether it means that there is a large correlation between an x and y, large kind of independence in x and y, or not. And it turns out that covariance is not so good for this. What is much better is a correlation, right? So for correlation, we have a formula correlation of x and y is equal to covariance of x and y divided by the square root of the variance of x multiplied by the variance of y. So in other words, divided, so it's the same thing as saying that it's covariance of x and y divided by the standard deviation of x, standard deviation of y. So we compare it with the product of the standard deviation. And this is the right thing to do, because if you scale the random variables, you multiply x and y by some constants, then the variance will be multiplied by the product of this constant. But the correlation, no, it will stay the same. Right? So it's invariant to the multiplication by number, by scaling of the random variables. And so now if you want to calculate this thing, you'll need to know what's the variance of x and what's the variance of y. And so this is again kind of, well, more or less lengthy calculation, but so variance of x. So it's by definition expectation of x squared minus expectation of x squared. So we'll need the expectation of x. We already know that it's equal to 3/4. And so what's the expectation of x squared? Well, again, so you'll need to kind of do a calculation. So expectation of x squared is equal to the integral from 0 to 1. Here's x squared multiplied by the marginal density of x. So 3x squared dx. So, well, this is an easy integral. So it's 3x5 divided by 5 from 0 to 1. So it's equal to 3/5. Right? So this is the expectation of x squared, and for the variance of x, we have this 3/5 minus 3/4 squared. So, and if you calculate it, let's see what we'll get here. Well, you'll get something something like a 0.00375. And well, you can do this about the same calculation for the variance of y. So let me skip kind of doing this. So it turns out that this is equal to 1/5. This would be expectation of y squared minus 3/8 square would be equal to 0.059. Right? So, and from this thing you can calculate that the correlation is equal to the, okay, so using this formula, plug in the numbers. Okay, so this formula, plug in the numbers, and you'll find that the correlation of x and y is equal to 0.397. And well, this says to you something, this is kind of more meaningful, right? So it says that it is equal to 0.39, and it's a pretty big number, right? It says that there is a big dependence between x and y. And you think about why this is big dependence, you look, well, there is a kind of, well, two factors here. Well, the most important factor that this is a triangle. Okay? So it's a triangle. So if you know that you have a some values of x, then you can get that so you know that x is small, right? So if x is small, then y is also must be small, right? So from the fact that it is a triangle, that if x is small, then y cannot be larger than x. So it's also small. So at least this forces these two random variables move in the same direction. Right? And also there is also kind of this factor 3x, but well, kind of overall, this is maybe less important. So if it would be just 3x, but the region would be rectangular, then they would be independent, as we saw in the example, kind of, right? So this, because 3x is factorizes, so it may be not so kind of moving. It's not moving force behind the independence here. All right. So okay. So this is example of how the things are calculated. Right. So now another thing which we want, so that I want to talk about is this is a little bit more esoteric. So kind of I would prefer maybe to skip it, kind of, right? But so this is in the book. So in some of the or in some of the homeworks. Right? So let us look at this, and this is just a conditional variance. Right? So kind of another topic is a conditional variance. Variance and the law of iterated variance. Okay, so what's the conditional variance? Conditional variance is a very simple thing, right? So conditional variance, well, it's a variance of a random variable, conditional variance of y given x. It's a variance of y if you know that x have some realization. So it's a variance with respect to conditional distribution. Okay, so so by definition, it's equal to expectation of y squared given that given x minus expectation of y given x, so all this stuff squared. Okay, so it's a kind of a definition of a variance, but now we have that x is known. So maybe kind of if I write down more kind of in the terms of kind of how to calculate it, then it will be something like that. So you'll have that the variance of y given that x is equal to x small. Right? So it's for every specific value of x, you have a different variance. Right? So it's equal to the integral of y squared, and here the integral would be of the range of y given that x is equal to x small. is integral of y squared, so we're writing the first part here, multiplied by conditional density of y given x. Here's y given x, and integral over dy. Okay, so it's the first part, and the second part it will be minus square of the integral over the same range. So we're okay, so just kind of the same thing. So range of y given x is equal to x. Okay. And here you'll have it, here's y, f of y, x, y, x. So this is very logical thing. So it's kind of just kind of, so the first thing is the expectation of y, but you calculate it with respect not to the marginal density of y, but with respect to the conditional density of y. Right? And the second thing, so this is a square. This is expectation of y given x, kind of by definition again. Right? So now this is a function of x small. You can see that it's a function of x small. So conditional variance. So the conditional variance is a function of the condition. Right? So the function of, so this conditional variance is a function of x. Right? So now we have a very useful formula before, which said that which is called the law of iterated expectations. So just a reminder, so law of iterated expectations. And then we saw it in the form that expectation of x was equal to expectation of conditional expectation of maybe kind of, well, maybe let me write here as y kind of, right? Expectation of y it is equal to conditional expectation of y given x. Right? And well, this is some function of x. You can take another expectation with respect. So you first of all calculate expectation of y given some all specific values of x. And after that, average over these values of x. So this was this formula, right? So it turns out that this is very, in many cases, very useful. Sometimes it's kind of, it can be used in other form, kind of, well, kind of maybe kind of useful to mention that you can also write it as another formula of a similar thing. So if you have some function of y and x, yeah, so this is just some function of x and y. Right? And you want to calculate what's the expectation of this function, you can also use this thing. So you can calculate expectation of conditional expectation of f of y x given x, and after that calculate this expectation. It's useful because it says to you, if you want to calculate expectation of some function of x and y, you can fix x. Right? And for every x, calculate what's the expected value of this function. Right? So kind of, well, useful kind of sometimes to do it, because if you fix x, then you can use the calculation often becomes simpler, right? And after that average over x, right? So now, this is a law of iterated expectation. This is the form we studied. This is another form which is kind of sometimes very useful. Okay, so maybe here I should write to be consistent. Or maybe here, let me write it again. So x and y. Right? And another, so the question is maybe kind of, what about variance? Can we say that the variance of y is equal something in terms of a conditional variance? So maybe can we do the same trick? So we want to calculate the variance of y. And so can we kind of fix x, calculate the conditional variance, right, of given every x, and after that average over x? Well, so we suggest writing it with something like that. It's expectation, so it's average, And here's a conditional variance, variance of y given x. So for every value of x, calculate the variance of y, and after that average over all possible values of x. So it turns out that this is not quite right. So there is additional terms which is not captured here. Right? So it's not enough. It turns out that this is not kind of enough. So there is another term which says, well, we also need to look at the variance in the conditional expectation. So variance in the expectation of y given x. Now let me kind of check that I'm not, yeah. Okay, so this is a kind of a formula which is called the law of the conditional, the law of the iterated variance. So this is the law of iterated variance. I'm not going to prove it, so there is a proof in the lectures, but it's a it's a little bit cumbersome variance. Iterated variance. So maybe I'll give an example, and this is also kind of a little bit interesting example, not totally straightforward. So here's an example. Right? So suppose that we have the following situation. So we have a factory that produces some gadgets. Right? So some parts maybe to the maybe some gadgets, maybe some parts to kind of a smartphone, something like that. And so and it's like the problem like this. So we have a control of the quality, and we want to figure out what's the something about the defective parts, about the number of the defective parts. So in here we have a situation that x is the number of defective parts in a sample of n equals say to 20 parts. Well, kind of this is a clear situation. This is binomial random variable, right? So we know about this. This is just kind of a binomial random variable. So we can look at the first part. It's defective or not defective. Defective, it's our success. We found a defective part. So we do it 20 times. So this is binomial experiment, right? So kind of, well, with some probabilities. So, okay, so we know that x in principle it's distributed as a binomial, right? So we think about that every kind of part are independent from another. So it's x is a binomial with n equal to 20 and the probability p. The interesting thing in this example, when we think that p is also random, p is random, is a random variable, Well, and one possibility is kind of where p is different from day to day, right? So kind of on some days, so everyone is a kind of drunk and kind of, well, kind of p is very large. Kind of on other days, well, kind of after the, well, kind of, well, so everyone is sober and kind of a p is small, right? So p is a random variable. Right? And we actually can model this. So as a statistician, we are able to model this situation, and we say that it's actually p has some distribution. So we take kind of on kind of some specific day, then we can model this p as a better distributed random variable. So p is between 0 and 1. So we'll need some variable which is kind of we need some distribution which is between 0 and 1. We can use uniform, but we use more general. We use a beta. So beta with a parameter alpha is equal to 1, and parameter beta is equal to 9. So this is a valid distribution between 0 and 1. And then after that, we say what is expected value of x, right? And what is the variance of x. Now, so how we calculate the expectation of x? The expectation of x should be equal to, well, it's a binomial random variable, so it should be equal to np. So in our case, should be equal to 20p. Right? But this is this depends on p. So in principle, what we'll need to write down that it depends on p. So it's a conditional probability. So it's e of x of p. So this is not quite right. So this is not quite right thing because p here is also random. Right? So p here is random, so it's e of x divided by p is equal to 20p. So this is more right thing to write down. Now, and after that, if you recognize that this is a conditional probability, conditional expectation, then we can write that actually e of x should be equal to expectation of e of x given p. So we'll need average overall 20 p's. Okay? So it's equal to expectation of 20p. So you can write it by, it's equal to 20 multiplied by expectation of p. And after that, we are looking up what's the expectation of a beta random variable. And okay, so expectation of a beta random variable is alpha divided by alpha plus beta. Right? So it's equal, in our case, is equal to 21 divided by 1 plus 9. So it's equal to 2. Right? And this is in principle this is we could do it maybe intuitively. Right? And say we know that expectation of x is equal to 20p. What's the average value of p? The average value of p is, well, it's equal to expectation of p is equal to 1/10. Right? We know that the beta distribution where we use this formula, this is average value of p. It's equal to 1/10, so it should be 20 multiplied by average value of p should be equal to 20 times 1/10 should be equal to 2. Right? So it's not very surprising thing. But this is how we can calculate it using the law of iterated expectation. So what about the variance? Right? Variance of x. Right? And this is in this case, well, if you think about it, this is not a quite obvious problem, how to calculate the variance. You know that this is equal to npq, right? So, right, in principle, right, should be, it's equal to npq, so it should be equal to so np1 minus p. Right? And again, so you recognize this is not quite right what I wrote here. It's not a variance. It shouldn't be raw variance. It should be variance of x given p. It's a conditional variance. So if p is fixed, then this is variance. So now suppose we use the we don't know how to use this conditional, the law of iterated variance. So in this case, we would say, all right, so on average, p takes value equal to 1/10. Right? So it should be good approximation. I'll just plug in this 1/10 in this formula. Right? So so this is a a reasonable attempt, right? So reasonable heuristic, right? So heuristically, E of p is equal to 1/10. So we would put out, so should be something like a 20 multiplied by 1/10 multiplied by 1 minus 1/10. So what is it? It's equal to 20 multiplied by 9 divided by 100. Okay, so what is it? It's 1.8. So this is a heuristical kind of our heuristic approximation for the variance. Now let us do it rigorously using the law of iterated variance. Right? So rigorously. And we use this formula. So we use that the variance of x should be equal to expectation of the variance of x given p plus variance of expectation of x given p. So what it means in our case? It means that this should be equal to expectation of this is, let me use 20 instead of n, so 20 p minus p squared, right? So this is p1 minus p, 20p minus p squared. Right? So this is inside, it's a variance of x given p plus variance of and what is our expectation of x given p? It's equal to 20p. Right? So now here's a little bit more complicated calculation. So first of all, look at variance of 20p. Right? Well, we don't remember it, kind of we'll need to look it up, but for the beta random variables, variance of the beta random variable is equal to, oh, I need to look it up, right? That's kind of, let me see. Variance of the beta distribution is equal to alpha multiplied by the beta, alpha plus beta squared, alpha plus beta plus 1. So we can kind of Google the beta random variable and find out what's this variance. Right? It's equal to this one. In our case, it's equal to 1 multiplied by 9, 1 plus 9 squared, 1 plus 9 plus 1. So it's equal to 9 divided by 100. So here's 100 multiplied by 11. So something wrong here. So so it's not wrong, but kind of here's a 20p, right? So variance of 20p is equal to 20 squared. So 20 squared multiplied by 9 divided by 100 multiplied by 11. So it's equal to 400 divided 100. Right? So 4 multiplied by 9 divided by 11. So 36/11. So this thing, we calculated it using formulas for the variance of a beta random variable. It's equal to 36 divided by 11. 11, yeah. What about this thing? So what's about expectation of 20p minus p squared? So again, we can write kind of use the formulas for the beta, but we can do it also directly kind of with this calculation. So this thing is equal to 20 multiplied, and here's integral. So it's integral of 0 to 1. Here's p minus p squared. And after that, I write here the density of the beta distributed random variable. So p, here's alpha minus 1. So alpha is equal to 1. So there is no p here. Okay? So no p. Right? And 1 minus p, so maybe p to the power of 0. 1 minus p, here's beta minus 1. So beta is equal to 9. So 1 minus p to the power of 8. Right? dp. And also remember that we also have a constant in the beta distribution. Right? The constant is equal to gamma alpha plus beta divided by gamma alpha gamma beta. Right? In our case, it's equal to gamma of 11, sorry, gamma of 10 divided by gamma of 1 gamma of 9. Right? So it's equal to 9 factorial divided by 8 factorial, so it's equal to 9. Right? So here is also we'll need to multiply by 9 because this is a constant in the beta density. Right? And so after that I continue, this is equal to 20 multiplied by 9, integral from 0 to 1. So here is a p 1 minus p. So it's p0 is just 1 kind of, and here we'll have 1 minus p to the power of 9, because here's 1 minus p comes also from this formula. So 1 minus p to the power of 9 dp. So I'll need to calculate this integral. And so we can do it directly, right? So kind of it's easy to integral, so it's easy to calculate. Or you can say, all right, this is a beta integral, so its value is equal to so gamma, and here you'll need to use something like, so here's so you use the formula that we integral from x alpha 1 minus x, so alpha minus 1, 1 minus x beta minus 1 dx is equal to gamma alpha gamma beta divided by gamma alpha plus beta. Right? So it's equal, okay, in this case, alpha in this case is equal to 2, right? So it's equal to gamma of 2. Beta in this case is equal to 10, so gamma 10. And here's 10 plus 2, so 12. Gamma of 12. So it's equal to 2, here's 1 factorial. So gamma of 2 is equal to 1 factorial. Gamma of 10 is equal to 9 factorial. Divided here is equal to 11 factorial. Okay, so it's equal to 1 divided by 11 multiplied by 10. All other things are cancelled out. And so altogether this is equal to 20 multiplied by 9 divided by 11, 10 divided by 10. So it's equal to 18 divided by 11. And so we calculated that this portion here is equal to 18 divided by 11. So, okay, so this calculation gives us that the variance of x is equal to 18 divided by 11 plus 36 divided by 11. So it's all together, so sum up, we'll get a 54 divided by 11. So, well, it looks like kind of, so what is it kind of? So it's around 4.909. And so the point, kind of a punchline here is that this is 4.9, it's around 5. And so a heuristic calculation that we did, it's equal to 1.2, it's equal to 2. So rigorous calculation give you much, much larger variance than the heuristic calculation. And this is just because the portion which comes from the portion which comes from the variation in P is very large, kind of. So in heuristically, we assume that P is equal to its average value. And so, and calculate the variance of X given that P is equal to its average value. But it turns out that there is also a portion which comes from the fact that P is kind of, it's changing kind of from day to day. So there is also a portion which comes from that P is very small on one day, is P is very large on the other day. And it turns out that this is a very significant portion. And so it turns out that this is kind of, it's like kind of contributes more than the half of the variance to the variance of X. And so, right, so okay, so I understand that this calculation is, well, kind of looks kind of difficult, right? So it's a straightforward calculation, so kind of just a bunch of integral. There is also this gamma things, but you can calculate this, for example, this integral without using any gammas, just by hands, right? So just polynomial in P, right? So it's a cumbersome calculation, but it's useful calculation. It gives you something which was not expected, and so it gives you an expected answer, right? So it's available. This formula is a valuable formula, right? So it's useful in statistics. And again, so it's a more complicated formula, maybe not so necessarily but it's useful. And so you should be aware about the existence of this formula, how to calculate the variance of X. If you can calculate variances, conditional variance in specific cases. So specific varialization of the random variable X, conditional variances. Okay, so that actually finishes the portion of the course, so which is could be on the exam. Okay? So after that, we will talk a little bit more about specific models of multivariate random variables, about multinomial distribution and the Gaussian distribution. But this is a kind of portion which we stop right now. Right, so if you have a question about this material or about the coming exam, so don't hesitate to ask. Otherwise, thank you for coming. So have a nice day. See you on Friday.
Thank you. Professor, do you mind if I ask a question on a practice exam?